In today's lesson, we're going to look at adding and subtracting rational expressions. First, let's talk about some vocabulary. Whenever we talk about a complex fraction, that's a rational expression that has a fraction in the numerator or the denominator. For example, we could say 3 divided by 2/5. That's an example of a complex fraction. Or if we had x minus 4 over x as our numerator, then our denominator fraction could be something like 5x. So there's two examples of complex fractions. Then least common multiple, that's a term that you've seen since elementary school. The least common multiple is the product of the prime factors, each raised to the greatest power that occurs in any of the expressions. In our example here, 12xy squared, if we took all the prime factors of 12, that would be 2 times 2 times 3 times x times y. So this is our prime factorization. And then 15 would be 3 times 5 times x times x times x times y. So to come up with our least common multiple, we would want to take all the prime factors, 2, 2, 3, x, and y squared. And then in the next one, we've already used a 3 here, so we don't need another 3. We don't have a 5 in the first, so we need a 5. And we need we already have 1x, so we don't need that x, but we need 2 more x's, and we already have 2 y's in the first factorization, so we don't need those. Multiplying all of those together, because it's the product of the prime factors, that would be 2 times 2 times 3 times 5, so 60, and then x cubed, and then y squared. So 60x cubed y squared would be our least common multiple. Then when we add and subtract fractions, if you have the same denominator, say you were going to add up a divided by c and b divided by c, because they had the same common denominator c, we could simply add a plus b. Now the same thing works if we're subtracting those fractions, so it would be a minus b divided by c. But when we have fractions with different denominators, let's say a divided by b, and I'm adding or subtracting c divided by d, then to be able to combine them, I need a denominator of b times d. So the a needs to have a d, and the c needs to have a b. So then we can add or subtract a times d plus or minus b times c, because I'm using that well-chosen one, that idea here again, so that the left fraction needs d over d, and our right fraction needs b over b, and we end up with that situation. So let's give some of these a try. I want to be able to find the least common multiple for the expression 2x plus 4 and the expression x squared minus x minus 6. So I want to factor x minus 3 and x plus 2. And then to find the least common multiple, we would take the product of the prime factors. So that would be 2, and then x plus 2, and then x minus 3. And you can see we've got an x plus 2 in the first factorization with the 2, so we need those 3 terms multiplied together. And if you wanted to multiply and expand that out, that would be 2x squared minus 2x minus 12. And I don't need that parentheses there. 2x squared. So either this answer or this answer would be appropriate. In part B, for the x squared plus 3x minus 4, that would factor as x plus 4 times x minus 1. And the second trinomial, we can factor that as x plus 4 times x minus 2. And then the third trinomial is a perfect square trinomial, which is x minus 2 quantity squared. So I'm going to write it out. And we want one of this and one of these, and we already have that one. And we want that one, and we already have one, and we need that one. So the least common multiple for these three trinomials would be the product of x plus 4 times x minus 1 times x minus 2 quantity squared. So least common multiple. In our next example, we want to add the two fractions, and in the first one, we're going to be missing a factor with the x minus 1. So we're going to think of the idea of a well-chosen one when we factor that second fraction. Our denominator is looking like that. So we need to give this fraction on the left, we needed to give it a well-chosen 1, and that's in the form x over x. So our numerator is going to be x squared plus x and x times x minus 1. Then our numerator over here is 2 and x times x minus 1. So they both have the same denominator, which gives us the ability to add the numerators together and combine our two fractions. So we have x times x minus 1 in the denominator, and they're asking us to state any restrictions on the variables. So you can tell from the beginning that our restrictions are going to be at positive 1 and at 0. So x cannot be 0 and x cannot be positive 1. So we've got those two restrictions. In part B, the second denominator, we can pull out a negative sign and make that y squared minus 16. So this just becomes a subtraction problem. The first fraction is y minus 9 over y squared minus 16. And if we take out that negative and flip that around, you can then move that negative sign up to the numerator or replace this positive sign, that plus with that negative, and make our problem a subtraction problem. And then we can combine like terms. So we've got y minus 9, and you've got to distribute that minus to both terms here. So we're going to have a minus y and a plus 7 over y squared minus 16. So y minus 9 minus y. So we're going to add the opposite here and the opposite here. Those y's are going to disappear. And negative 9 plus 7 leaves us negative 2 with y squared minus 16 in our denominator. Make that look a little nicer. So y squared. And then our restrictions, we're going to look back to the beginning. And our restrictions would be where y squared minus 16 is 0. That leaves us with y not being negative 4 and y not being positive 4. So we're setting that argument of the denominator equal to 0, and wherever y squared is 16, taking the square root both positive and negative, y cannot be positive or negative 4. In example 3, we're going to need to factor the denominator on the right fraction and figure out what's missing. So the factors of that trinomial would be x minus 2 and x minus 1, which leaves the fraction on the left. We're needing some well-chosen 1 there, and that's going to be the missing factor x minus 1. So we want x minus 1 as our fraction. Whoop. And I'm going to go ahead and distribute that. So x squared plus 2x minus 3, when we multiply this x minus 1 times the x minus 3. And then I'm going to subtract 6x and subtract negative 7. So we're adding 7 over our common denominator, x minus 2 times x minus 1. Adding like terms in the numerator gives us x squared, and then 2 minus 6 is negative 4, and 7 minus 3 is positive 4 over our common denominator. Then we want to think about factors of 4 that could add up to be negative 4. And again, that is a perfect square trinomial. So 2 times 2 would give us positive 4 if they were both negative 2's, subtraction. And then negative 2 and negative 2 would add up to be 4 in the middle. And we have a common factor in the top and the bottom, so we can simplify by removing that common factor. And what do we have there then? We could have x minus 2 divided by x minus 1 is our simplest term. And the restrictions would be restricted at positive 1. We can't have positive 1, and we can't have positive 2. So these are our restrictions here. In part B, when you factor the right fraction, we would have factors of 5 times 1 would multiply to be 5, and then outside and inside, 5x and 1x would add up to be 6x. So our fraction on the left is missing the factor of x plus 1. So we want to give this left fraction x plus 1 divided by x plus 1. This is what I'm calling my well-chosen 1. Then using the distributive property twice, we have x squared minus 1, and then minus x and minus 3, since it's a subtraction problem. And all of that is divided by x plus 5 times x plus 1. So in our numerator, we have x squared minus x minus 4 divided by that common denominator, x plus 5 times x plus 1. And I don't believe there's any factors of negative 4. When I multiply together, that would add up to be negative 1. So that's our simplest form. And then our restrictions are going to be negative 1 and negative 5. So we can't have x negative 1, and x cannot be negative 5. Now, when we want to simplify a complex fraction, you can do one way. One method is to simplify the numerator and the denominator separately to get a single fraction expression in each. So let me make up an example here. Let's say we have x over 2 and x over 3, and we're adding those, and then we're going to divide by 1/5. So using this, I'm calling this method number 1. This is method number 1 on your notes. So we can simplify the numerator, and the numerator can be a 6 for the denominator. So if we multiply each fraction by its well-chosen one, we have 3x plus 2x divided by 6, and then that fraction is divided by 1/5. So writing that sideways as a multiplication problem, we have 5x over 6 divided by 1/5. And when we put that as multiplying by the reciprocal, we have 5x over 6 times 5 over 1. So simplifying, we got 25x divided by 6. So that's our first method. And then method 2, we're going to find the least common multiple of all the denominators. So let's make up another example. Let's say 3 over x plus 1/2, and we're dividing that by 2 over x minus 3/4. So if we had a complex fraction that looked like this, we can clear all of the fractions by using some well-chosen one where it's going to eliminate all of the problems. So here it looks like we need a 4x on top and bottom. So that's our n over n, or what we're calling our well-chosen one. And combining those together, if we go ahead and write it out, let's see, we're thinking 12x divided by x for 4x times our first fraction. And then 4x times 1/2 is going to be 4x over 2. And then in the bottom we have 8x divided by x and 12x divided by 4. And I'm doing that to make a point here. So you can see that x over x is eliminated. The 2 divides 4, and we end up with a 2x here. Again, the x over x is gone, and 4 divides 12, and we end up with a 3x here. So we've done the eliminating all of the denominators. And that's going to give us 12 plus 2x in the top fraction, and 8 minus 3x for the bottom fraction. And we've simplified that complex fraction. So we got 2 examples to try, and in this first one I'm going to use method 1, and we'll use 2 over 2 times our x, and then the plus 1/2, we'll clear that fraction that way. And then the bottom, we'll do the same thing. We'll give x a 7 over 7 multiplied by that x, and then minus 1 over 7. So we're getting a common denominator in the top, which is 2x plus 1 divided by 2. And then in the bottom, we've got 7x minus 1 divided by 7. So I'm going to write it horizontally. And then we can multiply by the reciprocal, which is 7 divided by 7x minus 1. So combining all of that together, we've got 14x plus 7, because I'm using distributive property here. And then 2 times 7x is 14x minus 2. And if we wanted to state the restrictions, we would not be able to have 1 over 7 from our original problem. So I'm looking back here. We can't have 1 over 7 in order to keep division by 0. Okay, so there's that. And then in part B, we can use method 2 on part B, and let's think about our common denominator for the entire, all 4 fractions would be an xy divided by an xy. And again, so we don't make any mistakes, let's multiply each one so we can see what's being eliminated. So 3xy divided by x is going to help us eliminate the x's. And then moving to the next one, 4xy divided by y. We'll get rid of these y's. Then in the denominator, we have 4xy divided by x, so the x's cancel, and then minus 3xy divided by y, and the y's are eliminated. So putting all of that together, we have 3y plus 4x divided by 4y minus 3x. And then thinking about our restrictions, we would not be able to have x be 0. We wouldn't be able to have y be 0. And then when we get down here on the end, solving that denominator for 0, we would not be able to have y equal to 3/4 of x, because that would also cause division by 0. And then here in example 5, we've got some challenging ones, so these are a little difficult. In this case, I want to multiply x plus 1 with this fraction over here, so I want x plus 1 over x plus 1 times that first fraction. And then this side needs an x over an x, so 2 over x plus 1 needs an x over an x. This is method 1. And in the bottom, we need 3, and this fraction needs an x plus 1. So we've got 3 divided by x minus 1, and he needs an x plus 1 over x plus 1. And then the second fraction has an x plus 1, and he needs an x minus 1 over an x minus 1. So we're going to multiply across the top, right? So that's going to give us, looking over here, x squared minus x minus 2, and then coming to this side, plus 2x, and their common denominator is x times x plus 1. And we're going to divide that, moving down to the denominator fractions. We're looking at this row, so we've got 3x plus 3, and then looking over here, and I'm thinking about this minus, so we're going to think about adding the opposite. So negative 1 times x and negative 1 times negative 1. And then divided by our common denominator, x plus 1 times x minus 1. So looking back to our first fraction, if you have x squared and this x, that's going to give us x squared plus x minus 2. And I believe we can factor x squared plus x minus 2. So we want to think about x squared plus x minus 2 can be factored down to factors of 2 that add up to be positive 1. So we could think about x plus 2 times x minus 1 there. So this turned out to be very simple like this. And then that denominator on the bottom. And then if we multiply by the reciprocal, so we have the x minus 1 and the x plus 1 from the denominator is now in the numerator, and we've got 3x minus x, so that's 2x plus 4. In fact, that can be factored, so we want to take the 2 out, so 2x plus 4 can be factored as 2 times x plus 2. So removing common factors, we have an x plus 2 in the numerator and denominator, and an x plus 1 in the numerator and the denominator, and multiplying all of those together, We have x minus 1 quantity squared, because there's 1 here and 1 here, and then 2x on the bottom. So that's our simplified combined answer. And then lots of things to consider. So we've got to go back to the beginning. We can't have in here, we can't have a 1. We can't have a negative 1. So we can't have a 1. We can't have a negative 1. We can't have a 0. And we can't have a negative 1. So we already did that. And what happened? What else? And then down here, we can't have a negative 2. So lots of restrictions there. So we said we can't have a negative 1 or a positive 1 or a 0. And then when we got down here, we canceled this x plus 2, so we can't have a negative 2. And I think we got them all there, so lots of restrictions there. And our last example. Okay, now this one really is a challenge, so we want to factor the numerator, x minus 3, and x plus 2. Factor the denominator. 7 times 2 would be 14. And we're getting very lucky there, so we could eliminate these two. And then we're going to divide by the factors of this polynomial, so that's x plus 5 times x plus 1, and then this denominator would be x minus 7 times x plus 1. So before we get too far in, we can go ahead and simplify that down some, get rid of this and this, and then combining those fractions, we've got x minus 3 divided by x minus 7, and we're going to multiply by the reciprocal, so x minus 7 goes to the numerator, and plus 5 goes to the denominator. So these factors are gone. And this one wasn't so difficult, was it? We've got x minus 3 over x plus 5 is our simplified term. And we're going back to the problem. So everything that makes these factors 0, they're not allowed because they're in the main denominator. You see how I'm looking at that? So we want to go look at all of those factors. So that's everything over here for our restrictions. So we wouldn't be allowed to have negative 5, negative 1, and positive 7 from that set. Now, when we go look at this, anything that makes this denominator 0 would be restricted. So again, we have the 7, which we already have here. And we can't have negative 2, so we've got to add that one. Can't have negative 2. Negative 2. I wrote positive 2. Negative 2. And I think that's all. That was a big lesson. See you next time.